Hello friends, I welcome you in lecture number 5 on higher order ordinary differential equations. In previous lectures we have discussed how to solve homogeneous linear differential equations. From this lecture onwards we are going to solve non-homogeneous linear ordinary differential equations. We will discuss the methods for solving non-homogeneous linear differential equations with constant coefficients. So before we proceed further, we understand one notation. Suppose this derivative with respect to x, say d by dx, is denoted by capital D. This D is known as differential operator. So we will use this differential operator to denote derivative with respect to x. So if we consider d by dx equal to capital D, then dy by dx can be written shortly as capital dy. Similarly, second derivative with respect to y, that is d square y by dx square, equal to d by dx of dy by dx, and if we use this d by dx equal to capital D, and if we consider dy by dx equal to dy, then this becomes d square y, that is second order derivative with respect to x is denoted by d square y. Similarly, nth order derivative of y with respect to x is denoted by d to the power n y. So we will use this operator notation whenever required. Now we discuss how to solve non-homogeneous linear differential equation with constant coefficients. So first we consider standard form of nth order differential equation with constant coefficients. Here a1, a2, an are constants. This rx is non-zero function of x, so that this equation number 1 is non-homogeneous. And here yn denotes the derivative of y with respect to x, or it is nth order derivative of y with respect to x. Similarly, this is n minus 1th order derivative of y with respect to x, and so on. So to solve this non-homogeneous equation, first we will consider right hand side equal to 0, and we will consider the homogeneous differential equation corresponding to this equation number 1. So if we consider right hand side equal to 0, then we obtain this equation number 2, which is homogeneous linear differential equation with constant coefficients, and we know how to solve this equation. So the general solution of this equation number 2 is known as complementary function. Shortly we will denote by capital C dot capital F. So this general solution of equation number 2 is known as complementary function of given non-homogeneous equation 1, and we will use this notation y suffix h to denote the complementary function. H stands for homogeneous, so y suffix h means it is the general solution of the homogeneous differential equation corresponding to given non-homogeneous equation. Now after that we will find out particular solution or particular integral of equation 1, which we will denote by y suffix p, p for particular. So to find out particular solution, we have different methods that we will discuss one by one, but this particular solution is always free from arbitrary constants. So first we have to solve the homogeneous differential equation corresponding to given equation. The general solution of that homogeneous equation is known as complementary function. Then we have to find out particular solution of given equation, which is denoted by y suffix p. And once we obtain these two, complementary function and particular solution or particular integral, the general solution of given non-homogeneous equation is nothing but sum of complementary function and particular integral. So that is y equal to yc, that is complementary function, plus yp. So again this yc is a general solution of corresponding homogeneous differential equation, and yp is any solution of 1 containing no arbitrary constants. That means yp is a particular solution, it has no arbitrary constants. So we have already discussed how to solve this homogeneous differential equation. So the only thing remains is how to solve or how to find out the particular solution or particular integral of given differential equation. For that we have different methods. These are the different methods that we are going to discuss one by one for finding out particular integrals. First we will discuss some shortcut methods for finding particular solution. Then we will go for these specific methods known as method of undetermined coefficients and method of variation of parameters. So again we repeat here, if we want to solve this non-homogeneous differential equation number 1, then first we consider the homogeneous differential equation corresponding to this equation 1. For that we will consider right hand side equal to 0 and we will obtain this homogeneous differential equation. The general solution of this homogeneous differential equation is known as complementary function. So first we will find out complementary function for given differential equation. After that we will find out one particular solution or particular integral of given equation. So to find out particular integral we are discussing different methods, and the general solution of given differential equation is nothing but sum of complementary function and particular integral. So today we are going to start with shortcut methods of finding particular integral, then we will go for these two methods one by one. So for shortcut methods, first we consider this standard form of non-homogeneous linear differential equation with constant coefficients. Here right hand side is a non-zero function of x and this a1, a2, an are arbitrary constants. Now first we write down this differential equation using that operator d. So if we consider d raised to n for nth derivative, then this nth derivative is replaced by d raised to n times y plus a1 times n minus 1th derivative is replaced by d to the power n minus 1 y. Similarly y dash is replaced by dy and so on. So we have written another form of this given non-homogeneous equation. Now if you observe this bracket, it is nothing but function of capital D. So we denote this bracket by function of D, say f of D, where f of D is nothing but this polynomial function in capital D. So f of D is a polynomial in D. So this equation number 2 is another form of non-homogeneous differential equation 1. Now we know how to find out complementary function. For that we will solve this homogeneous differential equation. Now for particular integral, we are interested in particular solution, that is we are interested in the particular value of this unknown function y which satisfy this differential equation 2. So suppose we consider y equal to 1 over f of d times rx. So if we substitute this value of y in this equation, then we can see, if I substitute y equal to this in the left hand side of this equation, I will have f of d y I replace by 1 over f of d rx, then I will obtain rx. That means this value of y which is free from arbitrary constants, it is particular value of y. So this value of y satisfies this equation number 2, and this value of y is free from arbitrary constants. So therefore this is particular solution or particular integral of equation number 2. So that we denote by y suffix p. So from equation number 2 we can write that particular integral is y suffix p equal to 1 over f of d rx. So this is the formula for particular integral. Now depending upon the nature of this right hand side function rx and this operator, we will see how to find out particular integral. Now these shortcut methods are applicable for particular right hand sides only. So they are applicable if our right hand side is exponential function, that is e raised to ax. If our right hand side is polynomial function, that is x raised to n or in powers of x, or if our right hand side is sine or cosine function, and sum and product of all these functions is allowed. So for different right hand sides, we have different shortcut methods. We have different formula for particular integral if right hand side is exponential function, polynomial, or sine or cosine, or combination of all these. So we will discuss one by one all these special right hand sides, but we will remember that these shortcut methods are not applicable for every differential equation. They are applicable for particular right hand sides only. So we are going to discuss all these cases one by one. We will first discuss how to find out particular integral if right hand side is exponential function. Then we will go for trigonometric functions, sine or cosine, and then we will go for polynomial functions and some other cases. So today we discuss this particular integral when right hand side is exponential function. So suppose right hand side is exponential function, say e raised to ax, where a is a constant. Then to find out particular integral, we will start with this formula. We know that this is a particular solution of given equation, which we denote by y suffix p. So we have this formula yp equal to 1 over f of d rx, and here rx is exponential function e raised to ax. So if our right hand side is exponential function, then we will remember that we will put d equal to a, where a is the coefficient of x in this exponential function. So we will put d equal to a in this polynomial function in d. F of d is a function of d. So in this function we will replace d by a and we will obtain f of a. Now if value of function f of d at d equal to a is non-zero, then we will keep it as it is, and we have particular integral equal to 1 over f of a e raised to ax if f of a is non-zero. Now suppose f of a becomes 0 if value of f of d is 0 at d equal to a, then we will differentiate this f of d with respect to d. That means we will find out f dash d. F dash d means derivative of this function capital f of capital D with respect to d, and we will multiply this by x, so that we have written here. Suppose f of d becomes 0 if we put d equal to a, then we find out f dash d, and we find out value of f dash d at d equal to a, and if this value is non-zero, then we consider 1 over f dash a e raised to ax, but here we multiply with x. So particular integral is 1 over f of d e raised to ax equal to x times 1 over f dash a e raised to ax if f of a equal to 0 and f dash a is non-zero. So we understand this with the help of example. Suppose we want to find the particular integral of this differential equation y double dash plus y dash plus 5y equal to e raised to minus 2x. So first we write this in terms of notations of capital D. So y double dash is replaced by d square y dash is replaced by dy, and we take y common, so we have written this equation in another form: d square plus d plus 5y equal to e raised to minus 2x. Now for particular integral, we consider yp equal to 1 over f of d, which is 1 over d square plus d plus 5 e raised to minus 2x. Now if we compare with e raised to ax, here a is minus 2. So we find out value of this function at a equal to minus 2. So if we put a equal to minus 2, we have minus 2 square plus minus 2 plus 5. Okay, here we are putting d equal to minus 2 in this function of d, and this is going to be 4 minus 2 plus 5, and this is going to be 7. That is, value of function at d equal to minus 2 is 7 and it is non-zero. So we keep 7 as it is, and this is our particular integral, because value of function is non-zero at d equal to minus 2. Now we consider this problem: y double dash plus 5y dash plus 6y equal to e raised to x. So this we can rewrite in terms of capital D as d square plus 5d plus 6y equal to e raised to x. So particular integral is yp equal to, we consider this on right hand side, and 1 over d square plus 5d plus 6 e raised to x. So if we put x equal d equal to 1, here coefficient of x is 1, then we have non-zero value. This is going to be 1 plus 5 plus 6, that is 12. So this is our particular integral. Similarly, if our right hand side becomes 0, for example, if we have this differential equation y double dash minus 2y dash plus y equal to e raised to x. So this we can rewrite in terms of d as d square minus 2d plus 1 y equal to e raised to x. So now particular integral is 1 over d square minus 2d plus 1 e raised to x. Now if we put coefficient of x, which is 1, if we put d equal to 1 here, we can see it is going to be 0. So we have to differentiate with respect to d here. Derivative of d square minus 2d plus 1 with respect to capital D is derivative of d square is 2d minus derivative of 2d with respect to d is minus 2, and here we write x, and once we differentiate we will multiply by single power of x. Now we again check, we put d equal to 1, here coefficient of x is 1, so if we put d equal to 1, then this becomes 0 again. So for that again we differentiate with respect to d, and here we have to multiply with x, so we have x square, and here we have e raised to x. So this is our particular integral. So whenever we obtain 0 in the denominator, after putting d equal to a, we will differentiate with respect to d, and once we differentiate with respect to d, we will multiply by x. So if I am differentiating one time, I will multiply by x. If I am differentiating two times, I have to multiply by x square, and so on. So we will remember this formula. If right hand side is e raised to ax, yp equal to 1 over f of a e raised to ax if f of a is non-zero. That is, we put d equal to a in f of d, and if it is non-zero, then we keep it as it is. If we obtain 0, then we differentiate f of d with respect to d, we multiply by x, and if first derivative is non-zero, we keep it as it is, and so on. Suppose we have f dash a is also 0, then we multiply again by x, so we will have x square and 1 over f double dash a e raised to ax. So this is very easy. We just have to remember this rule or formula, that if right hand side is exponential function, we are putting coefficient of x in f of d. Now if right hand side is a constant, then also we can use this method, because we know that we can write 1 equal to e raised to 0x. So if right hand side is a constant, then also we will use this method, and in that case we have to put d equal to 0. For example, suppose we have 1 over d square plus d plus 1 and right hand side is 5. So 5 I can rewrite as 5 into 1, that is 5 into e raised to 0x. Now we take this constant 5 outside, and because we have e raised to 0x, we put d equal to 0 in this function of d, and we have 1 here which is non-zero. So we have 5 into 1 over 1, e raised to 0x is again 1, so that is 5. So if right hand side is 0, then we will right hand side is constant, then we will consider, suppose we have right hand side equal to b, then we will rewrite constant b as b times e raised to 0x, and then we will put d equal to 0 in f of d. So in this way, if right hand side function is exponential function e raised to ax, then we can easily find out particular integral simply by putting d equal to a in f of d, and we will take care that denominator remains non-zero. If denominator becomes 0 after putting d equal to a, then we differentiate with respect to x, we multiply by power of x. So this is about first case for shortcut method. In next lecture we will discuss how to find out particular integral if right hand side is either sine function or cosine function. So this is all about this lecture. I hope you like it. Thank you very much.